Tonight, we gather at the absolute edge of the human psychological domain to witness a slow, silent cosmic foreclosure, far beyond the sun-scorched, volcanically tortured rocks of the inner solar system, past the Vishal gas giants that stand as local gravity wardens, and deep within the unshielded, freezing abyss of the interstellar medium, a solitary machine is drawing its final physical breaths. It is coasting through an absolute desert of vacuum, a place where our sun has shriveled into nothing more than an exceptionally cold, brilliant pinprick of light, and where the ambient temperature of empty space sits just a hair above absolute zero. For nearly half a century, this fragile arrangement of aluminum, titanium, copper, and gold has served as humanity's most distant mechanical outpost. It has been our ultimate cosmic scout, translating the invisible radiation, magnetic currents, and plasma densities of the outer dark into data streams that have systematically rewritten our textbooks. As Voyager 2, launched during the late summer of 1977, Voyager 2 was built by a young, ambitious, and deeply divided species that had only recently learned how to slip the bonds of Earth's heavy atmosphere. Its original builders at the Jet Propulsion Laboratory gave it an operational warranty of 5 years, enough to complete a primary mission of studying Jupiter and Saturn up close. No one in that era predicted that this machine would survive the violent radiation belts of the gas giants, execute the historic Grand Tour to capture the first images of Uranus and Neptune, and subsequently punch through the heliopause into the unyielding ocean of the interstellar medium. But space is an unforgiving executioner, and the physics of radioactive decay are absolute. Inside the tracking stations of NASA Deep Space Network, specifically the Vishal 230-foot radio antenna dish operating out of the desert of Canberra, Australia, the telemetry monitors are showing a fatal shift. Steady, rhythmic pulsing of carrier data that engineers have monitored for 48 years is beginning to fracture. The craft's internal nuclear battery is dying, its structural heating systems are shutting down, and the signal-to-noise ratio is dropping toward a permanent flatline. We are standing on the precipice of a definitive historical boundary. We are about to watch our longest-running connection to the cosmos vanish into the random radio static of the infinite vacuum. We lost it forever tonight. On Dark Matter Nap, we trace the exhaustive, heartbreaking final days of Voyager 2. We will analyze the desperate engineering maneuvers designed to squeeze the last atom of electrical power from its decaying core, the unforgiving mathematics of its fading transmitter, and the poetic, eternal path this dead machine will trace across the Milky Way long after human civilization has faded into myth. Settle in, leave the distractions of Earth behind, and let's decode the final transmission to understand why Voyager 2 is positioned where it is tonight. We must travel back to an extraordinary alignment of celestial mechanics that occurred in the mid-1960s. Gary Flandreau, an aerospace engineer working at the Jet Propulsion Laboratory, discovered a mathematical anomaly in the orbital paths of the outer planets. He calculated that during the late 1970s, the 4 giant outer worlds Jupiter, Saturn, Uranus, and Neptune would arrange themselves in a rare, sweeping geometric arc on the side of the Sun. This precise configuration happens only once every 176 years. Without this alignment, a spacecraft intending to visit all 4 planets would require an impossible amount of fuel, resulting in a launch mass so heavy that no rocket on Earth could push it out of gravity. But Flandreau realized that a single spacecraft, launched at the correct trajectory window, could utilize gravity assists falling into the gravitational well of Jupiter. The craft could steal a tiny fraction of the planet's orbital momentum, slingshotting outward with increased velocity and a modified vector aimed precisely at Saturn. Saturn would then repeat the process for Uranus, and Uranus for Neptune. NASA capitalized on this rare window, designing the Grand Tour program. Voyager 2 was launched on August 20, 1977, slightly ahead of its sister craft, Voyager 1, which took a shorter, more aggressive path. The geometry of Voyager 2's path was designed to maximize planetary encounters, sacrificing speed relative to Voyager 1 to ensure that humanity could get its first close look at the ice giants. It was a trajectory calculated with absolute precision, where a deviation of just a few miles at Jupiter would cause the spacecraft to miss Neptune by millions of miles a decade later. Voyager 2 successfully hit every window, riding the gravitational currents of the solar system like a sailboat navigating a cosmic archipelago. Structurally, Voyager 2 is a magnificent testament to 1970s industrial utilitarian. It does not possess the sleek, aerodynamic contours of modern cinematic sci-fi ships, because in the vacuum of space, aerodynamic design is functionally irrelevant. Instead, Voyager 2 was built as a highly specialized, lightweight equipment bus engineered to protect its delicate electronic brains from micrometeorites, extreme cold, and planetary magnetic fields. The core of the spacecraft is a 10-sided, hollow aluminum structure known as the decagon bus. The central cavity contains the wiring harnesses, the attitude control gas systems, and the data processing computers. Mounted directly on top of this decagon is a Vishal, white parabolic dish antenna stretching 12 feet in diameter. This high-gain antenna is the mechanical link through which Voyager 2 maintains its directional radio connection with Earth across the multi-billion-mile gulf. Extending outward from the central bus are several specialized, rigid booms. Science Scan Platform Boom houses the imaging cameras, infrared interferometers, and ultraviolet spectrometers used during planetary flybys. Stretching in another direction is a Vishal, lightweight boom made of an epoxy glass structure that extends 43 feet away from the ship. This immense length was required to keep the highly sensitive magnetometers away from the magnetic interference generated by the ship's own central electronics, allowing them to measure the true, raw magnetic signatures of space. On the opposite side sits the power boom, holding 3 heavy cylinders that houses its nuclear batteries. The entire structure weighs exactly 1820 pounds, an optimized mass designed to balance payload capability with the lift limits of the Titan II Centaur rocket that hurled it into history. The computational architecture of Voyager 2 is primitive to a degree that challenges our modern understanding of technology. The spacecraft does not possess a single centralized microprocessor or an operating system like a modern computer. Instead, its brain consists of 3 redundant, discrete computer systems constructed out of hardwired, discrete logic components and magnetic core memory. These 3 systems are the Computer Command System CCS, the Flight Data System FDS, and the Attitude and Articulation Control System AUX. The total combined memory capacity across all 3 systems stands at exactly 8 kilobytes. To put this in perspective, a single low-resolution image taken by a modern smartphone requires thousands of times more memory than Voyager 2 used to operate its entire ship, process its scientific readings, and navigate across billions of miles of uncharted space. The magnetic core memory unit store data by physically changing the magnetic polarization of tiny, donut-shaped ceramic rings woven together by microscopic copper wires. Because this memory capacity was so small, Voyager 2 could not perform real-time data compression or advanced processing. Image entered by its cameras during the planetary flybys had to be written line by line onto an onboard digital tape recorder. Tape would then play back mechanically, feeding the analog signals into the flight data system, which converted the information into a slow stream of digital bits that were transmitted to Earth at a rate of just 115 kilobits per second at Jupiter, dropping to a sluggish 1.4 kilobits per second by the time it reached Neptune. It is a computer system designed with slide rules, executing pristine, clean code where every single bit of memory was fought for by the software programmers. The engine of Voyager 2's longevity is a quiet subatomic furnace located inside its 3 radioisotope thermoelectric generators, or RTGS. When designing a deep space mission intended to venture beyond the inner planets, engineers run into a brutal wall. Solar energy is bound by the inverse square law. As a spacecraft travels outward from the sun, the solar radiation density drops relative to the square of the distance. At Earth's orbit, solar flux is a comfortable 1361 watts per square meter. At Jupiter, it drops to 50 watts. At Neptune, it is less than 1.5 watts. Solar panels at that distance would have to be hundreds of thousands of square feet in size, creating an impossible mass that no rocket could launch. To break past this barrier, Voyager 2 had to bring its own internal stars. The 3 RTG cylinders mounted on the power boom are packed with spheres of the plutonium-238 oxide. Plutonium-238 is a radioactive isotope that undergoes steady alpha decay, releasing helium nuclei and shedding mass as it transitions into uranium-234. This decay releases a continuous stream of kinetic and thermal energy. The internal core of the RTGs gets so hot that the plutonium spheres glow with a dull, red heat reaching hundreds of degrees. Surrounding this glowing nuclear core are arrays of silicon-germanium thermoelectric couples. These thermocouples exploit the Seebeck effect when a temperature differential is maintained across two different semiconductors, keeping one side hot near the plutonium and the other side cold, facing the deep freeze of space. Electrons migrate across the boundary, creating an electrical current launch. This system generated 470 watts of electricity, an energetic fortune that allowed all 11 scientific instruments, the computers, and the transmitters to run simultaneously. But the rules of nuclear physics are immutable. Plutonium-238 has a fixed half-life of 87 years, and the thermocouples degrade continuously under the relentless radiation bombardment. The decline of Voyager 2's power supply follows a predictable, unalterable exponential decay curve. Because the plutonium fuel decays at a fixed mathematical rate and the silicon-germanium thermocouples degrade linearly over time, the total electrical power available to the spacecraft drops by approximately 4 watts every single year. Let's run the numbers on this slow-motion bankruptcy. 1977 launch, 470 watts available. Full functionality of all systems. 1989 Neptune encounter power had dropped significantly. Engineers had to carefully manage power sharing between the tape recorder and the radio transmitters to avoid an electrical brownout. 2018 Interstellar entry power had slipped far lower. Multiple science instrument heaters had to be turned off. 2026 tonight, Voyager 2 is operating on less than 240 watts of electrical power. To understand how desperate this situation is, you have to realize that 240 watts is less power than it takes to run a standard modern gaming console or a small television. Voyager 2 must use this dwindling reserve to run its central command systems, maintain its internal clock, drive its attitude control gyroscopes, and amplify the radio waves it beams back to Earth billions of miles. The mission controllers at the Jet Propulsion Laboratory have been forced to become extreme energy accountants. They monitor the power draw of every transistor down to the milliwatt. When the voltage drops too low, the central bus experiences an automated power reset, which would plunge the spacecraft into a permanent, frozen coma. Every decision made today is a calculation of survival time, choosing exactly which components to starve of electricity so that the heart of the machine keeps beating for a few months more. The greatest enemy of Voyager 2's voice is steadily expanding sphere. The power density of the signal drops in inverse proportion to the square of the distance from the spacecraft. Voyager 2 is currently located over 12.3 billion miles away from Earth. It has drifted so far into the outer dark that a radio signal traveling at the ultimate speed limit of causality, 186,000 miles per second, requires over 18 hours to make a one-way crossing from the ship to our planet. Say the time that originally crisp 23-watt beam completes its 18-hour journey across the solar system, it has been systematically pulverized by distance. The energy density that strikes the tracking stations on Earth has dropped to less than a fraction of a picowatt. A picowatt is $10, $12 watts, 1/trillionth of a single watt. The signal arriving from Voyager 2 is billions of times weaker than the ambient electrical noise generated by your television remote or a standard digital wristwatch. It is a subatomic ripple of electrons, a microscopic hum attempting to survive against the overwhelming background static of the universe. To capture a fraction of a picowatt signal from the edge of the solar system, humanity must deploy its most massive engineering eyes. This is the responsibility of NASA Deep Space Network, or DSN. The DSN consists of 3 major antenna complexes distributed around the globe in Goldstone, California, Madrid, Spain, and Canberra, Australia. But Voyager 2 presents a brutal geographic crisis that leaves most of the planet completely blind to its presence. During its final planetary encounter with Neptune in August 1989, Voyager 2 had to execute a highly aggressive flyby to study Triton, Neptune's largest moon. The trajectory required the spacecraft to dive close over Neptune's north pole. This maneuver acted as a violent gravitational slingshot, deflecting Voyager 2's vector downward, sending it south relative to the ecliptic plane, the flat disk where the planets orbit the Sun. Because Voyager 2 is screaming down into the deep southern celestial hemisphere, it has slipped entirely below the horizon for the tracking stations in California and Spain. The literal curve of the solid Earth acts as a permanent wall blocking their view. The entire responsibility for tracking, hearing, and commanding Voyager 2 rests on a single facility on Earth, the Canberra Deep Space Communication Complex in Australia. Within this facility stands Deep Space Station 43 DSS-43. This is a colossal, 230-foot-wide parabolic dish antenna, the only antenna in the entire southern hemisphere with a transmitter powerful enough to cut through the distance and a receiver sensitive enough to catch the craft's dying whisper. Even with the colossal 230-foot surface of Deep Space Station 43, catching a signal that measures in fractions of a picowatt requires cheating the thermal laws of chemistry. Every material in the universe that sits above absolute zero possesses thermal energy. The atoms inside the copper wires, aluminum waveguides, and electronic amplifiers of a radio antenna naturally vibrate, creating a chaotic movement of electrons. At room temperature, this internal molecular noise generates a radio hiss that is millions of times louder than the signal arriving from Voyager 2. The spacecraft's voice would be instantly obliterated the moment it entered the antenna's electronics. To bypass this barrier, the DSN utilizes extreme cryogenic engineering. The primary microwave receivers mounted at the focus of the Canberra dish are sealed inside a vacuum-insulated vessel and submerged in liquid helium. The cryogenic cooling system drops the temperature of the amplifiers to just 4 Kelvin 4 degrees above absolute zero. At this temperature, molecular movement slows down to an almost complete standstill. The electronic static inside the machine drops to near zero. This allows the antenna to achieve a clean baseline, separating the random thermal noise from the highly structured, digital carrier wave sent by Voyager 2. The incoming picowatt stream is amplified, digitized, and routed through fiber optic cables to the data processing centers. It is a system where we must freeze our own machines to hear a frozen machine screaming from the dark dot. Operating a spacecraft across interstellar distances introduces a profound shift in how we conceptualize cause and effect. In our daily lives, information appears instantaneous. You hit a key and a character appears. You make a phone call and a voice responds. But across billions of miles, the speed of light operates as a hard temporal wall. Voyager 2 is currently sitting at a distance Jahan C. Roshni or radio wave Koan John Main Lagbag 36 C40 Gant Ka Same Lagda High. Let's look at the operational reality this creates for the engineering team at the Jet Propulsion Laboratory. Imagine a scenario where a subatomic cosmic ray strikes a memory cell inside Voyager 2's attitude control system, causing a bit flip. The computer becomes confused and fires its hydrazine thrusters incorrectly, causing the spacecraft's high-gain antenna to drift off target by a fraction of a degree. The spacecraft detects the fault and logs an alert into its telemetry stream. That stream travels outward at 186,000 miles per second, taking 18 hours to cross the vacuum. The warning code does not register on the consoles in Canberra until 18 hours after the event took place. The engineers analyze the data, determine the correct software fix, and transmit the corrective command sequence back into space. That command wave must travel another 18 hours across the empty gulf. By the time the code actually arrives at Voyager 2's computer, nearly 36 hours have elapsed since the original error occurred. Mission Control is permanently reacting to the ghost of a spacecraft's past, operating across braided gulfs of time where a crisis can execute the machine long before its creators ever see the alarm. The baseline survival of Voyager 2 over its 48-year journey has been enabled by a systematic, brutal schedule of technological sacrifice. The spacecraft that flies through interstellar space tonight is a stripped, hollow shell of the machine that left Florida in 1977. The first major systems to be sacrificed were the visual imaging cameras. In August 1989, Voyager 2 captured spectacular images of Neptune's atmosphere, its great dark spot, and the nitrogen ice geysers of Triton. Once the spacecraft cleared the planet, its cameras were no longer pointing at anything but empty blackness. In 1990, NASA commanded Voyager 2 to execute a permanent shutdown of its scan platform. The electrical currents running to the wide-angle and narrow-angle cameras were cut. Heaters protecting the optical lenses were deactivated, and the cameras went dark. In the years that followed, the triage grew more severe. Engineers systematically deactivated the heaters for the ultraviolet spectrometer, the infrared interferometer, and the photopolarimeter. In 2020, to save 4 watts of power, they turned off the heater for the low-energy cosmic ray instrument. The temperature of the sensors dropped to an unbelievable 74 degrees Fahrenheit. The engineering team expected the instrument to instantly fail, but the rugged, vintage components defied thermodynamics. The frozen circuits kept running, continuing to measure interstellar particles from a sub-zero state. On November 5, 2018, Voyager 2 achieved its ultimate scientific milestone, crossing a boundary that had only existed in theoretical physics models. It broke through the heliopause and entered true interstellar space. The sun does not just emit light, it constantly radiates a supersonic stream of charged particles, protons, and electrons known as the solar wind. Solar wind flows outward in all directions, carving a visual magnetic bubble around our solar system called the heliosphere. The heliosphere acts as a vital protective shield, deflecting the high-energy galactic cosmic rays that bombard our sector of the galaxy. But as the solar wind expands outward, it eventually hits the interstellar medium, the tenuous haze of gas, dust, and magnetic fields left behind by ancient stellar explosions across the Milky Way. The heliopause is the hard boundary Jahan par sun ki solar wind ka pressure or interstellar medium pressure opa's main balance hojada high. It is the literal edge of the sun's magnetic empire. On November 5, 2018, Voyager 2 detected a sudden, dramatic drop in the density of solar wind particles. Within hours, solar particles vanished entirely, and the intensity of galactic cosmic rays surged significantly. Voyager 2 had plunged into the raw, unshielded ocean of the galaxy, leaving the solar cradle behind. The data returned burned by Voyager 2 during its heliopause crossing shattered decades of theoretical computer modeling. Scientists had built sophisticated simulations assuming the heliosphere was a clean, symmetric, spherical bubble surrounding the sun at a uniform distance in all directions. But Voyager 2 proved the architecture of our solar neighborhood is complex and warped. Voyager 1 had crossed the heliopause in August 2012 at a distance of 121 astronomical units. Voyager 2 crossed 6 years later at a distance of 119 astronomical units. While those numbers sound similar, the 2 spacecraft were traveling along completely different trajectories. Voyager 1 was heading northward relative to the ecliptic plane, straight toward the nose of the heliosphere. Voyager 2 was heading southward and toward the flank. The fact that Voyager 2 crossed closer to the sun proved that the heliosphere is asymmetric and flattened. It is shaped more like a blunt bullet or a cosmic teardrop. The front of the bubble is compressed by the sheer physics of the sun's velocity, the galactic center, at 490,000 miles per hour. Voyager 2 exposed the true morphology of our solar domain. We reside inside a warped, breathing bubble that deforms and oscillates in response to the invisible cross currents of the galaxy. One of the most profound mysteries solved by Voyager 2 involved the magnetic characteristics of the interstellar medium. Scientists had expected that the moment a spacecraft crossed the heliopause, it would detect a sharp, violent shift in the direction of the surrounding magnetic field. The sun's magnetic field lines are twisted into a spiral pattern. The galactic magnetic field, however, is generated by the collective dynamics of billions of stars across the Milky Way. The transition across the heliopause should have triggered a massive magnetic rotation. When Voyager 1 crossed in 2012, its magnetometer detected absolutely no shift in the field's direction. This sparked years of intense debate, with some scientists arguing that Voyager 1 hadn't actually reached interstellar space. But Voyager 2 settled the controversy. When it crossed the heliopause in 2018, its instruments detected a clear, distinct magnetic rotation of about 20 degrees. This revealed that the lack of rotation at Voyager 1 was a pure cosmic coincidence. At Voyager 1's specific crossing coordinate, the local galactic magnetic field lines happened to run completely parallel to the sun's internal field lines. Voyager 2's offset trajectory exposed the truth: the galactic magnetic field is structured, independent, and separate from our star. The cosmic ray data returned by Voyager 2 from outside the heliosphere introduced an unexpected anomaly that continues to challenge astrophysics models. Galactic cosmic rays are high-energy subatomic particles accelerated to relativistic speeds by cosmic shock waves. Scientists had predicted that once a spacecraft entered interstellar space, away from the deflecting influence of the heliosphere, cosmic rays would appear completely isotropic, meaning they would strike the spacecraft with equal intensity from every single direction. But Voyager 2's cosmic ray subsystem detected a profound anisotropy. Cosmic rays in nearby interstellar space are not moving uniformly. Voyager 2 measured a distinct enhancement of particle flux arriving from specific stellar coordinates, and a corresponding deficit from other directions. The data suggests that the intense magnetic structures of the galaxy guide cosmic rays preferentially from certain directions. Interestingly, both Voyagers measured a significant deficit of cosmic rays arriving from the direction of the galactic center, an unexpected finding given that the core of the Milky Way has the highest concentration of star formation. Our grasp on Voyager 2 is incredibly fragile, a reality highlighted by a near-fatal crisis that sent shockwaves through the Jet Propulsion Laboratory. During a routine command upload, an automated code string contained a microscopic formatting error. When Voyager 2's primary computer processed the instruction, it executed an incorrect directional sequence that commanded its attitude control gyroscopes to tilt the spacecraft's physical orientation by just 2 degrees away from its baseline vector. In our human scale, 2 degrees is an insignificant variation, the nudge of a steering wheel. But across a distance of 13 billion miles, a 2-degree shift is an absolute operational disaster. The narrow cone of Voyager 2's high-gain antenna tilted away from Earth. The focused beam of its picowatt signal missed our planet completely, shooting past into the empty void. Instantly, the telemetry screens in Canberra went black. Voyager 2 was suddenly deaf and dumb, screaming its data into an empty sector of space, entirely unaware that its creators could no longer hear its voice. For weeks, engineers utilized Earth's most powerful transmitters to send an ultra-high-power radio shout from the Canberra dish, packing massive amounts of wattage into a beam aimed at Voyager 2's estimated position, hoping the signal would bleed into the edge of the spacecraft's misaligned receivers. After a month of agonizing waiting, the strategy worked, and the link was restored. But it was a terrifying preview of the permanent silence that awaits us. Sometime within the next few years, likely before the decade closes, the electrical voltage output from Voyager 2's decaying RTGs will hit an absolute mathematical limit. It will drop below the absolute threshold required to maintain its processing systems and drive the radio transmitter. Before the spacecraft slips into an erratic state, NASA will execute a final, deliberate operational protocol, the Death Command sequence. This software package is already being drafted by the engineering team. It is a clean, systematic execution routine. Mission controllers will connect to the Canberra transmitter and beam the final code sequence across the solar system. When Voyager 2 processes the data packet, it will systematically deactivate its final operational scientific systems, powering them down permanently. Next, the code will instruct the attitude control system to engage its hydrazine thrusters for one last, continuous burn. This burn will exhaust the absolute remaining reserves of fuel, locking the physical orientation of the spacecraft in space, stabilize the ship's spin axis so that its high-gain antenna points directly at the projected coordinate of Earth for as long as mechanically possible. And then, the computer will execute the command to power down its own transmitter. The electrical switch will flip, and the radio wave will cease. Voyager 2 will be officially transformed into a silent, frozen phantom ship drifting through the cosmos. When the radio voice of Voyager 2 falls silent, the spacecraft does not cease to exist. It does not rust, it does not crumble, and it does not slow down. On Earth, our technology is at the mercy of our environment. Oxygen rusts our iron, moisture degrades our electronics, wind and water erode our grandest monuments. But in the deep, near-perfect vacuum of interstellar space, there are no air molecules to cause oxidization, no water droplets to cause short circuits, and no weather systems to degrade materials. Voyager 2 enters a state of pristine, permanent preservation that will outlast everything built on Earth. The spacecraft is currently coasting at a speed of roughly 38,000 miles per hour relative to the Sun. Because there is no atmospheric resistance or friction in a vacuum to slow it down, Newton's first law of motion dictates that it will maintain this exact speed indefinitely. It is an 18-20-pound artifact of human history frozen at the exact millisecond its power expired. However, over immense timescales, high-energy galactic cosmic rays will slowly alter the chemistry of the spacecraft's outer insulation blankets, turning the fabrics into a deep, scorched amber. Micrometeorites will occasionally impact the high-gain dish, carving microscopic craters into its metal. But Voyager 2 will remain a perfectly preserved mechanical mummy across an eternity of time, while popular science media often states that Voyager 2 has completely left our solar system. Astronomers operate under a much larger, more demanding definition of our stellar home. Voyager 2 has broken through the heliosphere, but it has not left the gravitational domain of our sun. To truly break free of its birth system, the dead spacecraft must cross the ultimate frontier, the Oort cloud. The Oort cloud is a Vishal, spherical shell consisting of trillions of icy bodies and comets that wraps around our entire solar system. It marks the absolute limit where the sun's gravity still holds sway over matter. Right now, Voyager 2 is sitting at a distance of roughly 132 astronomical units from the sun. It will take Voyager 2 another 300 years of silent, continuous coasting just to reach the inner wall of the Oort cloud. 3 centuries will elapse on Earth. Digital infrastructure will turn over, entire political structures will dissolve, and generations of human thinkers will live and die, all while the dead metal explorer slowly approaches the perimeter of this cometary desert. Once it enters the Oort cloud, the true scale of cosmic emptiness becomes apparent. The cloud is so immensely thick that Voyager 2 will spend the next 30,000 years traveling through its width. It breaks free of the Oort cloud's gravitational pull. Voyager 2 becomes an independent satellite of the Milky Way galaxy. It is no longer bound to the local dynamic of the sun. It is tracing its own orbital path around the supermassive black hole at our galactic core, completing a full revolution every 225 million years. Because it was deflected downward during its Neptune flyby, Voyager 2 is currently navigating a path through the southern sky heading toward the constellation of Pavo, the Peacock. Space is mostly nothingness. Stars are Vishal fusion furnaces, but they are separated by light years of absolute void. The mathematical probability of Voyager 2 ever crashing directly into a star or a planet is effectively zero. It could drift through the galaxy for trillions of years and never make a physical impact. In approximately 40,000 years, Voyager 2's vector will carry it within 1.7 light-years of a dim, red dwarf star known as Ross 248. Located in the constellation of Andromeda, 1.7 light-years is roughly 10 trillion miles. The gravity of Ross 248 will gently curve Voyager 2's trajectory before releasing it back into the cosmic stream. After it passes Ross 248, the dead craft will continue its cruise through space, eventually sliding past Sirius, the dog star, in roughly 296,000 years at a distance of 4.3 light-years. Even though Voyager 2's electronics will be completely dead and its radio transmitter powered down forever, it carries a specialized payload that ensures its mission as an ambassador of Earth remains active for billions of years. Bolted securely to its side structure is a 12-inch, gold-plated copper phonograph disc enclosed inside a protective aluminum cover. This is the Golden Record, curated by a scientific committee led by Carl Sagan. The Golden Record is an explicit message to any potential extraterrestrial intelligence that might retrieve the craft eons from now. Encoded within the physical grooves of its golden surface are 115 analog images portraying human anatomy, our architecture, and the geographic landscapes of our planet. It contains audio tracks recording the sounds of our biosphere, the song of a humpback whale, the laughter of humans, and the mechanical roar of a rocket launch. It carries spoken greetings in 55 different human languages and an eclectic musical library that spans from Bach and Mozart to the raw rock and roll energy of Chuck Berry. In about 5 billion years, our sun will expand into a red giant star and engulf the inner planets, erasing every building and trace of human history. But Voyager 2 will still be out there in the interstellar void, its gold-plated disk completely undegraded. It is an absolute proof that we mattered. To comprehend the ultimate destiny of Voyager 2, we must leap far past human history, past the lifespans of our planetary structures, and into the grand architectural evolution of our galaxy. In approximately 4 to 5 billion years, a Vishal structural transformation will reshape our sector of space. Our home galaxy, the Milky Way, is currently locked in a gravitational embrace with our nearest massive neighbor, the Andromeda Galaxy. Two Vishal systems are rushing toward each other at a speed of 250,000 miles per hour, driven by the inescapable pull of gravity. When the Milky Way and Andromeda collide, it will not be a violent smash of solid objects. Galaxies are mostly empty space. The distance between individual stars is so immense that during the merger, stars will simply slide past one another without physical impacts. Instead, it will be a slow, majestic gravitational dance lasting hundreds of millions of years. The shifting gravitational fields will distort the spiral arms of both galaxies, organizing the two structures into a singular, Vishal elliptical megagalaxy that astronomers call Milkowameda. Where will Voyager 2 be during this galactic rearrangement? The dead probe will be caught in the middle of this structural restructuring. As billions of stars shift their orbits, their collective gravitational waves will warp Voyager 2's linear trajectory. The craft might be slung inward toward the core of Milkowameda, or it might capture a specific gravitational vector that flings it outward via a massive slingshot effect. Voyager 2 could be completely ejected from the galaxy, sent out into the absolute isolation of intergalactic space. If Voyager 2 escapes the gravitational collapse of Milkowameda and floats into the intergalactic void, it enters the absolute final timeline of our universe, the crawl toward heat death or maximum entropy, over timescales that dwarf the entire history of human existence. The stars of the universe will exhaust their nuclear fuel. By 100 trillion years from now, the last red dwarf stars will burn through their remaining hydrogen resources and fade into white dwarfs, then black dwarfs cold, inert spheres sitting in absolute darkness. The era of starlight will draw to a close. Voyager 2 will float through this darkening cosmos, completely unaffected by the stellar shutdown. But theoretical physics models suggest that even solid matter has an expiration date. Grand unified theories of particle physics are correct. The protons that make up the metal inside Voyager 2 are not completely stable. They possess a massive half-life of roughly $10.34 to $10.40 years. Over these incomprehensible durations, protons will spontaneously decay. Atom by atom, molecule by molecule, the structure of Voyager 2 will slowly dissolve from within. The Decagon bus, the 12-foot high-gain antenna, and the golden record itself will slowly dissolve directly into a gas of subatomic particles. The machine won't crash, it will simply fade away, its constituent components integrating directly into the quantum fabric of an empty universe that has reached ultimate thermodynamic equilibrium. This brings us face to face with a profound, mind-bending philosophical realization. The loss of Voyager 2's signal is not an engineering failure for NASA. It is our species' definitive entry into deep, cosmic time. It is incredibly easy to look at this progression and feel a sense of profound, existential dread. When we realize that the last link to Voyager 2 will be broken, we feel a deep sense of loneliness. The spacecraft is a physical extension of human curiosity, and when its radio goes cold, it feels like we are allowing a piece of ourselves to die in an unresponding, cold matrix. But there is a transcendent, beautiful perspective hidden within this silence. Voyager 2 is the ultimate monument to human defiance. We are fragile biological organisms bound to a single planetary surface, but using nothing more than our intellect, our mathematics, and the raw chemical elements of our Earth, we managed to build a machine that will outlive our star. When the last telemetry bits flatline on the monitors at the Jet Propulsion Laboratory, do not look at it as a loss. Look at it as a graduation. Voyager 2 is breaking free of its connection to its creators to become a permanent structural component of the universe. It will wander the dark, not as a broken piece of junk, but as a sacred time capsule, preserving the music, the languages, and the architecture of our species across eons that haven't even happened yet. Thank you for joining me tonight on this massive, emotional, deep dive into the final days and the eternal future of Voyager 2 here on Dark Matter Nap. If this long journey into the deep dark challenged the way you view human legacy or made you appreciate our tiny, fragile place in cosmic time, please take a moment to like this video and subscribe to the channel. Which is what gives me the capability to continue making these late-night, immersive explorations into the great mysteries of our existence. The next time you walk outside on a dark night and look down toward the southern horizon, send a silent thought toward the constellation of Pavo. Somewhere out there, far past the warmth of the sun, past the edge of the light, and past the horizon of our voices, a tiny metallic ambassador is coasting smoothly through the eternal dark, carrying our collective heartbeat into the infinite night. Sleep well tonight, knowing that even in an expanding, empty void, a piece of what we are will live on forever. Good night, and may your dreams reach far beyond the uncrossable horizon. Now, let us turn our eyes back to a different cosmic reality, one that defines the true nature of spacetime itself. Tonight, we're going to explore a truth that defies what your eyes tell you when you look at the night sky. The universe looks full. Stars scattered across the darkness, galaxies swirling in cosmic spirals, nebulae glowing with light. But when scientists measure reality on the largest scales, they discover something terrifying. Almost everything is missing. Matter is vanishingly rare. The space between galaxies is growing faster every moment, and the forces tearing the universe apart are only getting stronger. At the end of tonight, you're going to understand why the universe is empty for a reason. What dark matter and dark energy actually do, and why this moment in cosmic history is fragile in ways most people never consider. Look up on a clear night away from city lights, and you'll see thousands of stars. The Milky Way stretches across the sky like a river of light. It's beautiful, and it creates an impression of abundance. All that light, all those stars, surely the universe must be packed with matter. But here's the problem. Every single star you can see with your naked eye is in our immediate cosmic neighborhood. The farthest stars without a telescope are maybe 15,000 light years away. That sounds far, but the Milky Way galaxy is 100,000 light years across. You're seeing less than 15% of your own galaxy. And your galaxy is just one of hundreds of billions of galaxies in the observable universe. Point a powerful telescope at what looks like empty black space between stars. Choose a region with absolutely nothing visible to the naked eye, just darkness. The Hubble Space Telescope did this in 1995. They pointed the telescope at a tiny patch of sky in the constellation Ursa Major. The patch was so small it would take 12 million such patches to cover the entire sky. In that tiny dark region, Hubble stared for 10 consecutive days. Long exposure after long exposure, gathering every photon that arrived. What did they find? Approximately 3,000 galaxies. Entire galaxies packed into a region of sky the size of a grain of sand held at arm's length. Every blob of light in that image is galaxy containing hundreds of billions of stars. This became known as the Hubble Deep Field, and it showed astronomers something profound. Everywhere you look, even in the darkest patches of sky, there are galaxies, billions of them. They repeated the experiment in other patches of sky. Same result, galaxies everywhere. So the universe must be full, right? All these galaxies packed everywhere you look. The universe must be dense with matter. But here's where we need to do the math. Let's calculate how much matter is actually out there. The observable universe is approximately 93 billion light years in diameter. That's the farthest we can see in any direction. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains somewhere between 10 million and 1 trillion stars, depending on the galaxy's size. The average is probably around 100 billion stars per galaxy. So 2 trillion galaxies times 100 billion stars per galaxy gives us roughly 200 billion trillion stars. That sounds like a lot. Now let's calculate how much space those stars actually occupy. A typical star like the Sun has a diameter of about 864,000 miles. Multiply the volume of a single star by 200 billion trillion stars and you get the total volume occupied by all the stars in the observable universe. Approximately $2.08 times 1032 cubic miles. That sounds enormous, but the observable universe has a radius of about 46.5 billion light years. Convert that to miles, and the volume of a sphere with that radius is approximately $3.06 times 1080 cubic miles. Compare those numbers. Stars occupy about $2.08 times 1032 cubic miles, while the universe has a volume of about $3.06 times 1080 cubic miles. Divide the first by the second, and you get the fraction of space occupied by stars, approximately 7 to 8 times 1049. That means stars occupy less than 1/quadrillionth of 1/quadrillionth of a percent of space. Let me put that in perspective. If you shrank the observable universe down to the size of Earth, all the stars combined would occupy a volume smaller than a single atom. Actually, much smaller than a single atom, more like a single proton. And most of a star's volume is empty space too. The nucleus of an atom occupies about 1/trillionth the volume of the atom, while the rest is empty space where electrons orbit. So even the matter in stars is mostly emptiness. Now let's look at the space within galaxies and between galaxies. The Milky Way galaxy contains approximately 200 billion stars. The galaxy is about 100,000 light-years across. The nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. That's roughly 25 trillion miles. So the distance between stars is thousands of times larger than the stars themselves. If you scaled the Sun down to the size of a grain of sand 1 mm across, the nearest star would be about 19 miles away, meaning 19 miles of empty space between 2 grains of sand. That's the typical spacing within our galaxy. Galaxies themselves are separated by even more dramatic distances. The Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years away. The Milky Way is 100,000 light-years across, so the distance to Andromeda is 25 times the width of the Milky Way. That's like 2 grains of sand separated by a football field if we're keeping our scale. And between the Milky Way and Andromeda, there are mostly just small dwarf galaxies and empty vacuum. Mostly, it's just empty space, nothingness, vacuum, darkness. And this is in our local group, one of the denser regions of the universe. In other regions, galaxies are much farther apart, separated by massive voids. Even counting all the stars and all the galaxies and all the gas and dust between them, we're still missing most of the universe. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma Galaxy cluster, a large group of galaxies about 20 million light-years away. Zwicky measured how fast the galaxies in the cluster were moving. He knew the cluster was held together by gravity with all the galaxies orbiting a common center of mass that doesn't emit light. He called it dark matter. Nobody believed him. Dark matter sounded absurd. Invisible matter that somehow had mass but didn't interact with light. It violated common sense, and scientists looked for other explanations, assuming Zwicky made a mistake. As more observations came in over the following decades, the problem persisted. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies. She measured how fast stars orbit the galactic center at different distances. In our solar system, planets closer to the Sun orbit faster than planets farther out. Mercury orbits faster than Earth, Earth faster than Mars, Mars faster than Jupiter. This makes sense because gravity weakens with distance. Galaxies should work the same way. Stars near the galactic center should orbit faster than stars in the outer regions. But that's not what Rubin observed. She found that stars in the outer regions of galaxies orbit just as fast as stars closer to the center, sometimes even faster. This made no sense unless there was additional mass in the outer regions adding extra gravitational pull mass that wasn't visible. Rubin's observations confirmed Zwicky's finding. Galaxies contain far more mass than we can see. The visible stars and gas make up only about 15% of a galaxy's total mass, while the other 85% is dark matter. Dark matter shows up everywhere astronomers look in galaxy clusters, in the cosmic web, and in the cosmic microwave background. Most of the matter in the universe is invisible. We can't see dark matter, we can't touch it, and it doesn't interact with electromagnetic radiation in any way. But it has mass, it curves space-time, and it exerts gravitational pull. It outweighs normal matter by a factor of about 6 to 1. For every kilogram of normal matter, the stuff that makes up stars, planets, and human beings, there are approximately 6 kilograms of dark matter. Current estimates suggest dark matter makes up about 27% of the universe's total mass energy content. Normal matter makes up about 5%. That means 95% of the universe's mass energy is in forms we fully understand. Without dark matter, galaxies, as we know them, couldn't exist. The gravity from normal matter alone isn't strong enough to pull gas together into the dense clumps needed for star formation. In the early universe, hydrogen and helium gas was spread uniformly. To form galaxies, this gas needed to collapse under gravity. Normal matter interacts with radiation, creating an outward pressure that resists collapse. Dark matter solves this problem because it doesn't interact with radiation or feel radiation pressure. Dark matter clumped together first, forming massive halos whose gravitational wells pulled normal matter inside to begin forming stars. Every galaxy sits at the center of a much larger dark matter halo. The Milky Way's visible disk is about 100,000 light-years across, but its dark matter halo extends at least 600,000 light-years. When you look at an image of a galaxy, you're seeing less than 10% of its total mass. The rest is invisible dark matter. Scientists have built sensitive detectors deep underground, trying to catch dark matter particles. The detectors are underground to shield them from cosmic rays and other surface interference. They're looking for extremely rare events where a dark matter particle passes through the detector and collides with a normal atom. Such collisions should be incredibly rare because dark matter barely interacts with normal matter. So far, these underground experiments have found nothing conclusive. Other experiments are searching for dark matter at particle colliders like the Large Hadron Collider, attempting to create dark matter particles by smashing normal particles together at high energies. If dark matter particles are created, they would fly out of the detector without leaving a trace, but their existence would be inferred from missing energy and momentum. Again, no confirmed detection has occurred. The leading theoretical candidate for dark matter is called weakly interacting massive particles, or WIMP. These would be subatomic particles heavier than protons, but interacting only through gravity and the weak nuclear force. Calculations suggest that if WIMP exist, they would naturally make up 27% of the universe, a coincidence called the WIMP miracle. But despite decades of searching, WIMP haven't been detected. This mystery makes the universe feel even emptier. Not only is space vacant, but most matter is invisible and unknown. And it gets worse because of dark energy. 1998, two independent teams of astronomers were studying distant supernovas, the exploding stars that briefly shine as bright as entire galaxies. They were focusing on Type Ia supernova, which occur in binary star systems where a white dwarf pulls matter from a companion star. When the white dwarf reaches a critical mass about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, it explodes catastrophically in seconds. Because they all explode at the exact same mass, Type Ia supernova all release roughly the same amount of energy and reach the same peak brightness. This makes them standard candles. If you know how bright an object actually is, and you measure how bright it appears from Earth, you can calculate its exact distance using the inverse square law. The two teams used these standard candles to measure the universe's expansion rate. They wanted to determine whether the universe's expansion was slowing down due to the gravitational pull of all its mass. Everyone expected the expansion to be slowing down. The question was simply whether there was enough matter to eventually halt the expansion and cause a collapse, or if it would expand forever at a decreasing rate. But in 1998, both teams announced a shocking result. The distant supernova were fainter than expected, meaning they were farther away than predicted. The only way this made sense was if the expansion rate of the universe was speeding up over time instead of slowing down. The universe's expansion is accelerating. Something is pushing space apart, counteracting gravity. We call it dark energy, but that's just a label for our ignorance. The simplest explanation is that dark energy is a property of space itself, representing a vacuum energy density that remains constant as space expands. As the universe grows larger, the total amount of vacuum energy increases because more space means more vacuum energy. This energy has a repulsive effect, creating a feedback loop. Expansion creates more space. More space creates more vacuum energy, and more vacuum energy causes faster expansions. When physicists calculate what the vacuum energy density should be based on quantum field theory, they get an answer that is $120 times larger than what we observe. This is the worst prediction in the history of physics, arguably the biggest unsolved problem in theoretical physics. Dark energy makes up approximately 68% of the universe's total mass energy content, meaning 95% of everything is stuff we don't understand. But there is another layer to this emptiness: cosmic voids. When astronomers map the distribution of galaxies across large volumes of space, they discover that galaxies aren't randomly distributed. They cluster together in filaments, and between these filaments are voids, enormous regions where almost no galaxies exist. The first large void was discovered in 1981 in the constellation Boötes. Astronomers found a region roughly 330 million light-years in diameter, containing only about 60 galaxies. A typical region of that size should contain about 10,000 galaxies, meaning the Boötes void has 99.4% fewer galaxies than expected. An observer on a planet in a galaxy in the center of the Boötes void would look out in every direction and see absolute darkness with the naked eye. The nearest significant concentration of galaxies would be more than 165 million light-years away. For comparison, our nearest large neighbor Andromeda is only 2.5 million light-years away. Voids are not rare, they are the dominant feature of the universe's large-scale structure. Most of the universe's volume is void. The Eridanus supervoid is about 1 billion light-years in diameter and corresponds to a peculiar cold spot in the cosmic microwave background. As the universe expands, voids are actively growing, expanding faster than the average rate because they have less matter to slow the expansion locally. The universe is evolving toward maximum emptiness. This structural evolution means that our window to observe the cosmos is closing. Because space itself is stretching, galaxies that are far apart appear to recede from each other. At a certain distance, this recession velocity reaches and exceeds the speed of light. It doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding. Light leaving a galaxy that is receding faster than light can never reach us. This defines the cosmological horizon, the edge of the observable universe. Right now, we can see galaxies out to a radius of about 46.5 billion light-years because the light left them billions of years ago when they were closer and expansion was slower. But as dark energy drives accelerating expansion, more and more galaxies in this horizon moving beyond our reach forever. In the far future, every galaxy cluster outside our immediate gravitationally bound local group will cross this horizon and fade from view. The cosmic microwave background will also redshift into long radio waves until it becomes completely undetectable. Future civilizations will look out and see only their own merged local galaxy, completely isolated in an ocean of emptiness, with no evidence that the Big Bang or other galaxies ever existed. This brings us to the ultimate fate of the universe: heat death. Heat death does not mean the universe gets hot. It means the universe reaches complete thermal equilibrium, a state of maximum entropy where all energy is evenly distributed and no more useful work can be done. Right now, the universe is far from equilibrium, stars are hot, space is cold, and differences in energy allow things to happen. But according to the second law of thermodynamics, entropy always increases. For the next 100 trillion years, stars will continue to form and burn, but star formation is already declining as gas is used up. By 100 trillion years from now, star formation will cease entirely, and the existing stars will slowly burn out. The universe will enter the degenerate era, populated only by white dwarfs, neutron stars, black holes, and cold planets drifting through dark space over time scales of $10, $30 years. Gravitational interactions will eject 90% of stellar remnants into intergalactic space, while the remaining 10% fall into central supermassive black holes. Galaxies will evaporate, then, over vast timescales. Even black holes will evaporate through Hawking radiation. A stellar mass black hole takes $10, $67 years to evaporate, while a supermassive black hole takes $10, $100 years. After $10 and $100 years, when the final flashes of evaporating black holes fade away, what remains depends on the stability of the proton. If theories beyond the standard model are correct, protons will spontaneously decay over timescales of $10, $34 to $10, $40 years. If protons decay, then all remaining solid matter, the cold black dwarfs and dead planets drifting in isolation, will slowly dissolve from within, atom by atom, over immense durations. Every remnant will vanish, turning into electrons, positrons, neutrinos, and photons spread across infinite expanding space. The universe will reach absolute heat death. No structures, no concentration of energy, and no events can ever happen again because there will be no energy differentials to power any physical process. the era of complexity, stars, and life is instantly the brief flicker at the very beginning of eternity. So you look at this expanding void and realize that emptiness is the permanent state of reality, while structure is temporary. But on human scales, right now, we live in the sweet spot where the universe is still rich, full, and maximally observable. We are a temporary pattern emerging briefly before dissolving back into the void. Let us shift our focus from the large-scale emptiness of the universe to the immense difficulty of moving between its scattered stars. Tonight, we are going to explore what it would actually take to travel to the nearest star system beyond our own Alpha Centauri. Alpha Centauri sits in the southern sky, located approximately 4.37 light-years away from our Sun. That is roughly 25 trillion miles, or 41 trillion kilometers. In cosmic terms, this is our immediate next-door neighbor. But for anyone who attempts to cross this gulf, the journey would be one of the most terrifying undertakings in human history. Alpha Centauri is a triple star system. Centauri A and B are sun-like stars that orbit each other closely, while Proxima Centauri is a small red dwarf that orbits the pair at an enormous distance. Proxima is actually the closest of the three to us, sitting at 4.24 light-years away from us. Astronomers discovered a planet orbiting Proxima Centauri, named Proxima Centauri b. It is roughly Earth-sized and orbits within the star's habitable zone where liquid water could potentially exist. This discovery transformed Alpha Centauri from an abstract target of scientific curiosity into a genuine destination. But before we plan a voyage, we must confront the reality of our current speed. Light travels at 186,000 miles per second, taking 4.24 years to cross the distance from Proxima Centauri to Earth. The fastest spacecraft humanity has ever built is the Parker Solar Probe, which achieves a peak speed of about 430,000 miles per hour by falling into the Sun's deep gravitational well. At that speed, you could travel from New York to Los Angeles in 6 seconds. If the Parker Solar Probe were pointed toward Proxima Centauri, the journey would take approximately 6,700 years. 6,700 years is longer than all of recorded human history. Our fastest chemical rockets are completely obsolete for interstellar exploration. To make the journey within a human lifetime, we must accelerate a spacecraft to a significant fraction of the speed of light, a feat requiring propulsion systems that currently exist only on paper. Scientists have proposed several exotic methods: nuclear pulse propulsion under Project Orion, which involves detonating atomic bombs behind a heavy shield, fusion drives that harvest the power of the stars, and antimatter engines that achieve 100% fuel efficiency through matter-antimatter annihilation. But each of these concepts faces monumental engineering barriers and political constraints that place them centuries beyond our current reach. The most realistic near-term proposal for reaching Alpha Centauri is the Breakthrough Starshot Initiative, announced in 2016. Instead of carrying heavy onboard fuel, this concept utilizes a massive, ground-based laser array to beam concentrated light at a lightweight solar sail. The spacecraft would be a tiny chip weighing only a single gram, attached to a highly reflective sail a few meters across. The laser array would blast the sail with 100 gigawatts of power for a few minutes, accelerating the tiny probe to 20% the speed of light. At that velocity, the probe would reach the Alpha Centauri system in just 20 years, but the challenges are staggering. The laser beam must remain focused with absolute precision on a tiny sail that is accelerating away at thousands of kilometers per second. Furthermore, because the probe is traveling at 20% light speed, it cannot slow down when it arrives. It would scream past Proxima Centauri b in a few hours, taking a few snapshots before flying off into deep space forever. And for a human crew, a gram-sized probe is useless. And humans, we need a massive starship capable of sustaining life for decades, a voyage that introduces severe psychological and biological hazards. If we construct a ship that can travel at 10% the speed of light, the voyage to Proxima Centauri takes about 42 years. 42 years is a massive chunk of a human lifespan. If you launch at age 30, you will arrive at age 72, having spent your entire adult life confined inside a metal hull flying through the void. The psychological toll of this isolation would be immense. Humans evolved to live in open, changing environments. Being locked in an enclosed space with the same small crew, eating recycled food, and breathing recycled air for 4 decades would test anyone's sanity. The crew would face physical degradation from long-term weightlessness, requiring the ship to rotate continuously to generate artificial gravity through centrifugal force. This requires the ship to be massive, with a rotation radius of at least 100 meters to keep Coriola's sickness tolerable. Power would have to come from nuclear reactors operating flawlessly for decades, and food would have to be grown continuously in automated hydroponic gardens where a single crop failure means starvation. Medical care would be entirely limited to whatever supplies were brought along, meaning the crew must manage the chronic illnesses of aging arthritis, heart disease, and dementia billions of miles away from Earth, and the interstellar void itself is packed with hidden dangers. At normal speeds, hitting a grain of sand in space is an insignificant event, but at 10% the speed of light, kinetic energy increases with the square of velocity. A single milligram speck of dust striking the ship at 10% light speed carries the kinetic energy of several kilograms of TNT, while a pebble weighing a few grams would hit with the force of a nuclear weapon. The ship would need massive forward shields to deflect these impacts, adding wazen and making acceleration harder. Space is also filled with cosmic rays, high-energy particles that can penetrate normal hulls, damage DNA, and drastically increase cancer rates among the crew. Communication with Earth would suffer from an expanding time delay. Halfway through the journey, a radio message takes over 2 years to reach Earth, and a reply takes another 2 years. Conversations become impossible, transforming into an exchange of historical letters across time. The crew would be culturally and socially frozen in the year they launched, while Earth moves on without them. By the time they arrive, they might find that Earth has developed faster propulsion technology and already established a colony there, rendering their 42-year sacrifice completely obsolete. Let's assume the crew survives the 42-year voyage and manages to decelerate into orbit around Proxima Centauri b. What would they find? Proxima Centauri is a red dwarf star, emitting less than 1% of the sun's light. Because the star is so cool, the planet must orbit incredibly close to remain warm enough for liquid water. Proxima Centauri b orbits its star at a distance of only 4.6 million miles, just 5% of the distance from Earth to the Sun. At this close range, the planet is likely tidally locked, meaning one side always faces the star in permanent daylight, while the other side is trapped in permanent darkness. The day side would be scorched, the night side frozen, and the only potentially habitable zone would be a narrow ring along the terminator where permanent hurricane-force winds blow due to extreme temperature differentials. Furthermore, red dwarfs produce powerful, violent flares that regularly bombard neighboring planets with intense radiation. Unless Proxima Centauri b has an exceptionally strong magnetic field, its atmosphere may have been stripped away long ago, leaving a radiation-blasted, lifeless rock. The crew might discover that their 42-year journey across the void has brought them to a dead world where survival requires living deep underground in pressurized bunkers. The scale of the cosmos is designed to separate us, establishing a physical quarantine that isolates intelligence. This isolation makes our current moment in human history incredibly precious. We exist in a brief cosmic window where the universe is still close enough to be observed and understood. We live in the Stelliferous era, the age of stars, which began a few 100 million years after the Big Bang and will continue for trillions of years. We are only 13.8 billion years into this timeline, meaning we are early explorers. The choices we make today, the technologies we develop, and the observations we record will define the baseline of knowledge for all future generations. We are the conscious eyes of our sector of space. We can look up, build telescopes, track Voyager spacecraft, measure dark matter, and calculate the acceleration of dark energy. We may never build starships that can cross the uncrossable gulfs to establish galactic empires. We may live out our entire history within the confines of our immediate solar domain, but our minds can bridge the distances that our physical bodies cannot. This capacity for understanding transformations our relationship with the cosmic void. Empty universe that is never observed remains just empty space. But an empty universe that is observed, measured, and comprehended by a conscious mind becomes a stage for existence. We are islands of complexity in an ocean of void, temporary structures emerging briefly in a cosmos trending toward maximum disorder. The great silence of the universe might simply be the physical reality of scale. Life is rare, intelligence is an anomaly, and the distances are too wide to bridge. This places an immense responsibility on our species. If we are the only conscious witnesses to this era of the universe, then we are the guardians of its meaning. If we destroy ourselves or allow our curiosity to die, the light of consciousness goes out in our sector of space, leaving the cosmos to continue its expansion in absolute, unthinking darkness. We must protect our planet, maintain our scientific continuous across generations, and keep looking up with humility and wonder. Must accept the limitations written into the physics of space-time while celebrating the extraordinary privilege of being here. Now, to decode its laws, consider what happens as dark energy continues its work. Billions of years from now, the galaxies outside our local group will have shifted so far away that their light will drop out of our view completely. The expanding space-time will stretch the incoming photons until their wavelengths move beyond our detection capabilities. The universe will systematically delete its own history from our sky. Future generations of observers will look out and see nothing but an empty void surrounding their local stellar group. They will have no physical way to discover that the Big Bang occurred or that trillions of other galaxies once existed. We are uniquely privileged to exist in an era when the cosmic record is still visible, when the clues to the origin and structure of the universe are written clearly across the night sky. We have a duty to record this data, to compile the ultimate map of the cosmos before the expansion carries the details beyond our horizon. Our science is our legacy, a monument built out of pure information that declares we were here. We looked at the darkness, and we figured out how it worked. It is the ultimate expression of human defiance against the oppressive scale of cosmic emptiness. And as we compile this data, our initial pioneer spacecraft, the Voyagers and Pioneers, will continue their silent trek through the dark. Long after their nuclear furnaces have gone out and their radio transmitters have fallen silent, these machines will drift as permanent monuments to our existence. They will slide past distant stars, cross cosmic voids, and orbit the galactic center for billions of years, outliving the very planet that launched them. They carry our music, our languages, and our geometry engraved on golden discs, floating like messages in a bottle across a silent galactic ocean. They are proof that we didn't just stay home, that we dared to reach out and touch the interstellar medium, even if only with our primitive machines. They represent our hope, our determination, and our goodwill in a vast, intimidating universe. Even if no alien hand ever retrieves them and no alien eye ever decodes their messages, their existence alters the cosmos. A universe that contains a silent capsule of human history is fundamentally different from a universe that is completely vacant. We have left our mark on eternity. We must remain humble in the face of this vastness. We pride ourselves on our scientific achievements. We have decoded the atom, mapped genomes, and detected gravitational waves. But when we look at the universe as a whole, we must admit that 95% of its mass energy content consists of dark matter and dark energy, things we fundamentally do not understand. We are like ancient navigators tracking the motions of planets without knowing what worlds they are. We can measure, predict, and calculate, but deep understanding remains elusive. The universe is a vast puzzle box that reveals its secrets slowly, requiring patience, dedication, and cooperation across generations. This mystery shouldn't discourage us, it should inspire us. It means that there is always more to learn, more to discover, and more boundaries to push. The great silence and the empty voids are open invitations to our curiosity, daring us to build better instruments, refine our theories, and keep exploring. We are an exploratory species, driven by an insatiable need to know what lies over the next hill, across the next ocean, or around the next star. And that drive is what makes us human. Thank you for joining me tonight on this epic, multi-hour deep dive into the terrifying mechanics of cosmic emptiness and the extraordinary journeys of our pioneer spacecraft here on Dark Matter NAP. If this exploration challenged your perspective on human legacy, or made you think differently about our fragile place in the space-time fabric, please take a moment to like this video and subscribe to the channel. Support is what enables me to continue creating these immersive, late-night journeys into the deepest mysteries of existence. The next time you walk outside under a clear night sky, look up at the thousands of stars and remember the math. Appreciate the view not because it is a crowded room waiting for us to arrive, but because it is a beautiful, fragile arrangement of matter emerging briefly within an infinite, expanding dark. Sleep well tonight, knowing that even on a tiny planet quarantined by light years of vacuum and dark energy, our consciousness has still managed to map the architecture of the cosmos. Good night, and may your dreams reach far beyond the uncrossable horizon.